Okay, going back to soft actor critique, one more last important feature of soft actor critique is, or an important discussion that we need to have, is how to choose, how to set the optimal, the best, or how to set the temperature parameter alpha, and setting it correctly is non-trivial. Moreover, the temperature needs to be tuned for each task, and during the learning process it also needs to be tuned over time to get the best performance. The magnitude of the reward differs not only across tasks, but it also depends on the policy, which improves over time during training. So as I said, it's also sensitive, the correct value is sensitive to the task, but also to the policy that evolves during the training on a specific task. The policy should be free to explore more in regions where the optimal action is uncertain, but remain more deterministic in states with a clear distinction between good and bad actions. So this tells us that it's not only that the temperature should change between tasks and as the policy evolves, but it also needs to be considered differently in different regions of the state space. And so in the paper they presented a simple approach to automatically adjust the temperature on each update step. So the alpha parameter, the temperature parameter, is updated automatically using a gradient descent step with some learning rate, where the gradient is defined on the performance of the current policy with respect to some target entropy that you still have to define, but it's just easier to define the target entropy, and then have alpha, it becomes auto-adjusted during the training process. For the full derivation and how to set the gradient in J with respect to alpha, please see the original paper. I don't have these specifics here in the slides. We won't go over them. So now we're ready to go over the full soft actor critique pseudocode. So initially we start with initializing the parameters for our Q network and our policy. So we have, as we saw before, we have two Q networks and one policy network. We initialize the target network weight to be similar to the initial targets at the beginning. We initialize an empty replay buffer. Then for each iteration, for each episode in the environment, and for each step in the environment, we sample an action from the policy, from our soft policy. Then we sample a transition from the environment. We apply the action and see what's the next state that we arrive at, and the reward, the immediate reward that we observe, and we store the transition in the replay memory pool. And for each update step, updating our policy and Q functions, we update the Q function parameters, we update the policy weights following the updates that we previously discussed. We adjust the temperature, as we discussed in the previous slide, and we update the target network weights, right? So this is exactly what I said previously. We don't set the target network to be equal to the target that we're constantly updating every C steps, as we saw in the DQN algorithm, but we do it over time in an exponential decay manner, right? So we have some step size, and we gradually make the target network closer and closer to our target that is constantly being updated. Then, finally, after the training process, we return the optimized parameters. And here are some results for soft actor critique. So we have we present two versions of soft actor critique, one with a learned temperature, the updated temperature, and one with a fixed temperature, so we choose a fixed alpha and run that. And these results are on 6 benchmark Mojuku domains, so robotic domains with continuous control, where the control is the force applied to each one of the robot's junctions. The x-axis here is the number of training steps, where the y-axis is the average return, the performance. So of course we want our algorithm to learn as fast as possible, shoot up as quickly as possible, and reach the highest performance as possible, right? Asymptotic performance. And indeed you can see that, let's say, look at one example, for instance, the humanoid example. We can see that soft actor critique with a fixed temperature performed best overall. It learned pretty quickly and it reached the best asymptotic performance, where soft actor critique with a tunable and learned temperature performs second best, and it's quite unstable compared to the fixed temperature soft actor critique. Also, we can see the PPO algorithm that performs less well, TD3 algorithm that doesn't perform very well here, and and DDPG that doesn't perform very well. I'll present DDPG in a second. By the way, TD3 is a variant of DDPG. I'll discuss this in a second. But these trends, the one that shows that soft actor critique with fixed temperature are the best, are not generally the seen overall, right? Oh, so here also the fixed temperature is the best. Here it's about the same as the learned temperature, but here in Walker 2D we see, and in humanoid V2 we see that actually soft actor critique with a learned temperature does perform best. Okay, so the results are mixed, but overall we see a very good performance for the soft actor critique algorithm.